start the recording. Okay. Okay, go ahead. So, can we go to the next slide, please? Yes. So this is the plan for today. We'll talk about the exceptions that we can throw them, we can catch them, how can we define an exception class, and then we will talk about the unique PTR, the one that I promised you some time ago that makes our life much easier and safer. So the C++ does provide a mechanism to help deal with the errors that are called exceptions, right? The detection of an error and its handling are separated, and it just once again makes our life easier in terms of how we can arrange it. So we deal with them separately. We deal with the detection and we define and we decide here for ourselves, do we throw exceptions or not? Because we might decide that we are not going to throw them and it will be dealt with somehow, or we can decide, yes, we will be throwing the exception, and then the user will have to handle them, right? They will have to catch them and to handle them. So the detection of an error happens that if our function finds some issue, right, finds an error that it cannot handle, then it should not return normally. That's our understanding behind it. So what we do, we should throw an exception indicating that something went wrong. Now, we do prefer to indicate exactly what went wrong. So you remember when we were catching the exceptions, sometimes we were calling the function what, right? We will see it today. So the what was reporting us the error message that was provided us with the moment when the exception was thrown. Now the handling means that we will compile a try block, right? So we will try an operation or try to call a function, and we expect some exceptions to happen there, right? So then we will conclude it with the catch block where we will be catching the exception. Now, I do have an example that I will show you, but before we proceed to it, you probably remember that when we were catching and throwing exceptions, we used the header std except, right? Like standard library exceptions. That basically defines a set of standard exceptions that both the library and programs can use to report common errors. Now, you will see it later on, but this is not the base class for the exceptions. So we do have something that this library, it's the classes that are defined in it inherit from. So, but we will see it later on. But what we have so far is we kind of have two sets of the classes in this library. We have the logic errors there. So we never used the logic error class, to tell the truth. What we used the invaded argument and we used the out of range, right? Those two we used, but we didn't use the domain error. We didn't use the length error. So these three are new to us. These two we saw before. The other set is a runtime error. And I'm not sure that we did use the range error. Okay, it wasn't the book, but I'm not sure that I used it in an example, right? But the runtime errors are usually the ones that are happening at the runtime. And we can see four types of them. So the runtime error, the range error, the overflow error, and the underflow error. But we didn't use any of them. So once again, I don't remember as me using it. So maybe the range error was in the examples that I left for you for the self-study, right? But I myself didn't use it, as far as I remember. Now, there are a little bit more of them, but not in here, in the base library that we will see later today. So these classes are inheriting from that. Now, if you recall the input-output streams, and you were working in the homework number 10 with the input stream, right, for the complex number. And if you play more with that and try to get those exceptions there, We don't have them. So at the time when the input-output stream library was created, nobody thought about the exceptions. So they were kind of added to them later on, and probably not in a very convenient way. So we do have the stream error states. These are the ones that we're using. You remember that fail bit, the bad bit, and so forth. So that is used in them. But by default, the input and output streams, they don't throw exceptions. They just raise the bits, right? So we covered it in the section 13.3, but I do remember that I made it as a recording. So make sure that you watched it. Now, Boost.org provides a library that supports exceptions. So it's a better support of the exception throws, but once again, it's also, I never used it. So I just kind of briefly read about it. So if you are interested, this one is a link to it. So if you click on it, it will be opening a link in your internet browser and you can kind of consider it. So in this term, this input output stream library, it's pretty weak on the things of what it can do. So the boost.org provides a better support for the input output. Now, let's ourselves see the examples that I kind of decided to have in the catching and throwing exceptions. And I will talk about this input and outputs, input stream exceptions, like what I was thinking of doing and what I couldn't do. So let me switch to the Visual Studio. I'll wait a little bit so to make sure that you have it up, because I know that the internet connection is not very stable today. So I loaded up this file, catching and throwing exceptions. You have it on our web page, and you should be able to, to get it later on. Now, what I am using in terms of the libraries here is the standard input output stream library, the exceptions library, and the vector. The vector I used later on at the very back, right, to show you what was it. It was out of range. It was out of range, right? Exception. This is the example we had some time back when we were just looking into the exceptions. So I just grabbed it, and I think I didn't even modify it. It's the same numbers here that I'm pushing, okay, and the same loop. So you can find it before, and this is kind of a review of what we had to have them all here together. But here is what I was thinking in terms of the input stream. I wanted to get an input from the user, the numerator and the denominator, to make up a fraction. And what I want to do is I wanted to catch the case where the user enters a letter from the keyboard, right? Not a number, but a letter from the keyboard. Let's say a letter F, right, a letter K, and so forth. And I tried to do it with catching the exception of invalid input. And it didn't work, obviously, because once again, the input and output stream library, they do not throw exceptions. They raise the bits, right? Those fail bits. You remember we had like 4 of them, right? The good bit, the bad bit, the fail bit, and then some other one. And we know how to read the states, right? So for example, here I reminded you how to check what's the fail bit set to, what's the bad bit set to. The fail bit is usually connected to the improper type of the input, right? And the bad bit is to the other cases. So this is what I'm doing here. I'm asking the user to provide the rational number by typing in the numerator and the denominator. Now, I did have an intention to have them in the try block, but once again, we cannot have it here, so we have to check the fail bit then. So usually the fail bit checks whether the type of the input is incorrect, and then I need to do it separately. So by providing the numerator, I right away check after, hey, what's the fail bit? Is it okay or something wrong happened, right? Now, since my intention was to provide something other than the integer there, that's why I'm checking the fail bit. So the fail bit will be raised if I enter the H or K, or even 2.9 is raising the fail bit, right? So this is what I do in this case. If it was raised, I'm saying that the type of the input is incorrect. I am not crashing the program. I'm just assigning the value of 0 to the numerator. Like, the base fraction, right? Okay, now this is me assigning the 0 to the numerator. And then I display what's the fail bit and what's the bad bit, right? Because usually those two play, right? And then after I did that, you see, unless we clear it, if you can recall, right? Unless we clear the states, the cin will not work, right? So I had to clear the states. Clearing the states, what it should do is it should reset the fail bit to 0, right? To false, that it's not raised. And the bad bit as well. And it's not only doing this, it's doing a little bit more to that. But here, I'm just checking the fail bit and the bad bit. So after I did the clear command, I'm checking what's going on with the fail bit and with the bad bit, right? And then what I found out also is it will not be enough for me to be able to proceed with the input, right? That the input that I provided is still in the input stream, and the very next cin command will kind of reread it, right? So what I have to do then is I have to clear the input stream completely. I have to get rid of everything there. And for that, we could use the command ignore, if you can recall it, right? We used it with the delimiter. We could use it without the delimiter by default, right? So I had to use it. Right now it's commented because I want to show you the behavior of the program. What will happen if I don't do it? And in order to avoid working with the vectors, let me also comment this one out for the time being, okay? So this one is commented so that we could work only with our numerator and denominator, okay? So check this one out. I'm going to run it. And, okay, so in here, instead of putting 4, I'm putting the H, right? So here what happens? I do see this report. This is the report over here. The type of the input is incorrect. The value of 0 is assigned to the numerator. This is the fail bit. It was raised, right? So I check it before I'm clearing it, right? The states of the input. Then after the clearing is done, you can see that the fail bit now is 0. So it's raised down, right? But then you see this input for the denominator, right? The denominator, and then automatically the type of input is incorrect. The denominator is set to 1. So you see, it didn't allow me to enter anything, right? So what it meant for me is that, hey, you know what? There is something still in the input stream and the cin is getting it, right? So that's why I had to use this command ignore to erase everything, right? To ignore everything from the input until the enter, right? Until the enter. And then it allowed me to enter the denominator. So not only I have to lower down the fail bits, right? And those errors, I also have to clear out the input. So you see, now it's waiting for the denominator to be entered. So for example, I can hit 7, right? So it was acquired and there are no more issues there. Now, if I were to use the, let's say the decimal, right? The decimal, it's not catching it, right? You see this, like what's going on, right? So it's not catching it, right? So I have to play more with it to catch this instance of what happens if I am providing a decimal value, right? Instead of the integer, what to do with that, right? So I have to take here of that case as well. And I did. So the code that I have right now is only catching the case if I provided the letters right there, like that. But it doesn't work if I provide the decimal instead of the integer, right? Now, and if we provide everything as we are supposed to, there are no error messages, right? So this is how we are not catching the exceptions, but checking the bits, right? Because input and output streams do not provide us with the exceptions by default. Okay, now, then I decided to work with the vector because with the vector, we do have exceptions thrown, but Not when we are using the square brackets, when we are using the at, right? So the square brackets do not throw the exceptions, right? They do not. Only the at operation throws the exception. So this is the one to use if we expect some issues there. And this is what I do. I created a vector of decimals. I'm pushing into the vector 1, 2, 3, 4, 5 values. And then I do this loop, which has 6 iterations, isn't it? 6 iterations. I'm starting with 0, I'm ending with the 5. So what it means is I'm having 0, 1, 2, 3, 4, 5, 6 iterations there. So I'm definitely going out of the range. So this is the type of the message, out of range here, right? I did it on purpose here. I'm using the STD. Let me see, maybe I don't need to, yes. So I'm using this. So I don't need to use the scope resolution. I could just do this, right? An STD I would use in case if I'm not including the entire standard namespace, right? So this is the command I was talking about, right? What? Like what happened? So when the exception is raised, it is equipped with a message to us, right? And that message we can retrieve by using the operation what, right? Okay, so let's run it. Let's run it. Let's provide good input for our fraction. And then here is the message that was sent us through those exceptions, right? So we have invalid vector subscript, right? So I'm not throwing the exceptions here. I was actually going to throw them, but then I did it in another code. So it's kind of misnamed a little bit. The file is misnamed. But what I could do over here, right? I could throw the exception. So if I decide to do that, right, I could throw the exception over here and I could call it that it's invalid input. I could call it just runtime error, whatever I decide to, and I could provide a message coming with it if I decide to do it. But I decided not to do it because then it will terminate the program for me, the main function. So usually when we are throwing an exception, it happens not in a main function, but in some helper function, right? In some standalone function, in some method, but not in the main, because in the main, we usually catch it, right? So that was the option for it. Okay, now I think the next topic for discussion is, yes, how can we define an exception class? And what you will see is I'm not doing the definition inside the main function, although I could do it just as a simple function. You will see it in the first example. I think over here I do it as a function and here I do it as a class. My memory doesn't fail me. So once again, we have options as always. We can inherit from an existing exception class, from anyone we decide to, or we could just not use any of the exceptions classes that we have and just create something like a toy function for us. And usually what I was told too is that the companies, sometimes they write their own exception classes. They do not use the ones that are built in C++ because they do not satisfy to what the company needs. So they create their own exception classes and you're using them, okay? So let's switch to the Visual Studio and give me a few minutes to include the files, existing items. Okay, so here they are. So actually this example I grabbed from the online resource. It was O'Reilly's book. It actually C++ cookbook, but it's connected to the C. So it's more like, the C level. No, I'm not using it as, okay. Yeah, it's not used as a function. I thought that I actually did it as a function, but okay, it's just a class. So it's a very, very basic class that is not inheriting from any of our exception classes. It was just named the extension. Oh, exception. It have a message to create when it is constructed. So, it's getting a message for the actual argument or actual parameter. It is storing it, right, as the exception message parameter. Here it is. It has a destructor because usually we do supply destructors. And what we will be doing later on, we could send a message, like we could see out something to display that, the destructor happened. Here we don't provide anything, just to kind of having it empty. But we could send the message to the display here if we wish to. And then we have this method, get message. So what we do here is we emulate that operation what. You remember, like the one that I called, right, in the previous example? So if I want to see what was the message of the exception, I will call the method get message. That's why we had to include this library string that will provide us with the string message for the return. So what it basically does, it returns that message that was stored when the exception was created, right? So here we created the exception. We recorded the message. It was sent to us through MSG, right? Message. And then with the get message, we display it. So here what we do, we imagine doing something wrong here and we just throw the exception, right? So we throw the exception. As you can see, I am just creating an instance of this exception class that I have over here with these message, right? So we did something wrong, it generated an exception, right? So this message that you see over here will be supplied through this argument into the attribute of the class, right? Data attribute. Okay, so we throw it and here we catch it. When we catch the message, not the message, when we catch the exception, we always catch it by the reference, right? And we can even add the const here if we wish to, right? That one, it's okay to do it here. And then we can read the message by calling the command here, right? We call the message. And also what we could do is we could use that error stream. You remember what's the difference between the C out and C error? That it's not buffered. Remember that, right? Because C out is usually buffered. So we reach the buffer and everything is displayed. Oh, it's the end of the program, so it's displayed, right? But the C error is not using a buffer, it's sending the message right away. So usually when we catch the errors, we do prefer to use the C error, right? Output. Okay, and then we say you threw an exception and then we get the message. Right? Now, this example I really liked because it shows you that we are not tied to the existing exception classes, right? We can build our own and work with it. So let's run it, but it's really silly because we cannot have a lot of the code here. We are just learning the structure of how things are working out, right? So over here, we threw the exception with this message. Let me move it over here, right? So this is the message that we supplied. So at the moment when we are throwing the exception, right? When we create this object, we provide the message. That's what I mean by saying that when you're working on throwing the exception, you send the message along of what's going wrong, right? You can throw several exceptions. So depending on the code, you can throw the exception with the message that, hey, invalid type, hey, invalid number of parameters, right? Different messages. And this will give more information to the person who is catching them. Okay. And once again, it's a two sides process here. Here, we are working on throwing them, right? And here, we're working on catching the exceptions. Okay, so let me show you another one which has more stuff in it because it inherits from something. I think it inherits from the standard, really base class, which is called exception. Removed and existing item, and this is the one. Okay. So, oh no, okay, I used the runtime error. Okay, runtime error. So in another example, I used just the base class. So you remember those runtime class errors that we used over here, the one that I mentioned to you. You see that ones, right? From the std accept library. So, this example, and once again, I just followed along with our textbook because it decided to inherit from the runtime error. The reason to it is that we want it to happen when the program is running, right? At the runtime. So it's very reasonable to inherit from the runtime error class. Okay. So I'm including the library. It's a public type of inheritance, right? And we call our new exception class division by zero. So we continue to work with that rational number, right? The numerator and denominator. And we want to create an exception when the denominator provided to us is a zero, right? Because we are getting the division by zero. Now, why so much fuss about it? Because it's no longer throwing exceptions. The C++ no longer is throwing exceptions when the division by zero is performed. It will return you either negative infinity or positive infinity. So it's no longer considered an exception, and sometimes we don't like it, right? So we do not want to get the infinity there, right? We do want the exception to be thrown, and we do want to catch it later on if it happens. So that's why we are talking about it. That's the reason of it. So, new exception class called division by zero exception. It is inheriting from runtime error class. And what it means is that it inherits its constructor as well. That's what we do over here, right? So the constructor of the division by zero exception is just calling the constructor of the runtime error with this message. Remember that we need to provide the message so that we could call the what method. And if we want to override that virtual function, because what is a virtual function? It's provided to us by the very, very base class, which is called exception. So we'll see today later, right? So it can be overridden here. I decided not to because I already provided the message here and I didn't have any particular need to override it. So I'm not doing it. But if we decide to do it, we can do it over here. We can override it. Okay. Now, and this one is a function which will be throwing the exception. Do you remember that I told you that if I throw an exception, I don't do it from main. In main, I usually catch it, right? So this is the function exactly like it is, from the book. I think I just called the class slightly differently, but this is a function that is returning a decimal value of division, numerator divided by the denominator. Both numerator and denominator are integers. And it is returning us a decimal number, right? So we don't want the infinity there. We want a statement, hey, that's the answer, or hey, you've got a problem. We should not divide by zero. That's why in case if the denominator is zero, I am throwing this exception. So look at how I do it. I just create an instance, right, of the division by zero exception class. I'm not sending any message. The constructor does it. So it's automatic message. I don't replace it with anything else, right? So it is whatever it is here, right? Division by zero. You see, I'm not expecting any parameters there, right? No arguments. Okay, so, and if everything is okay, we are returning the division of numerator by denominator. The only thing I have to do here is not to forget to convert. Since the double and integer types are very close to each other, we could use the static cast, right? So we don't need that reinterpret cast. And if we want the C style of it, then we will say, what was it? I think it was like this, double, it was like this, right? So this is the C style conversion, just the double. Static cast. Okay, and it's also what we used to do in Python. You remember we just used to say double or float or char and so forth. So now inside the main function, We're getting two numbers from the user. We are trying to call the function quotient. If everything is okay, the result is displayed. If something is wrong, then the only wrong thing that we could catch, that's the thing, that's the issue. We could catch only this. We could catch division by 0, right? So this is what we do. You see, this time I said that it's a constant, right? And in the previous example, I didn't. So of course, in general, we should put the constant here. But, when we are just playing and not paying that much attention to this, we could skip it. So once again, what does it mean? That although I get it by reference, I should not modify it, right? So I'm getting this division by 0 by reference, right? That's an access to the instance of the division by 0 exception class, right? So we read the message. Do you see the spot method called, right? So it will display exactly this message to us if that happens. But that's it. I'm not catching anything else, right? I'm not catching in other exceptions. For example, when I provided what is it? Like a key, right? Like a letter here, right? Or a letter here. I will not be catching it. So let's try to run the code to see what will happen if I provide different inputs. So if I provide 5 and 6, everything is well, the quotient is found and displayed. If I provide 0 for the denominator, right, then we are getting this message from our catch, right? Exception was thrown, that's the message, right? Now, if I provide a letter here, right, then you could see what is going on, right? The denominator was not asked from us. The quotient is -0, right? It's very interesting what was there, and we could run the debugger to see what was actually supplied, right, for the numerator and the denominator into the function. So let's run it. I'll put the breakpoint over here. So let's see what are the values that were provided to the function quotient, because when we step inside it, we'll be able to see what were they. Okay, so I'm doing the F, right? Okay, so here is the A. A was 0, right, after the input. And the B was this negative number. Now, this negative number is that garbage when the number is just declared, right? So here I just announced that I will have a variable of type integer, but I didn't initialize it. So usually when I'm not initializing it, it has some garbage in it. It's like this one, right? Now, if we go, and so it means that these are the two values that will be provided for the quotient, because if we step into the function, you're seeing now that the numerator is 0 and the denominator is that garbage, right? And because the flag was raised, the fail bit was raised, right? In here, right? The fail bit was raised when I entered the letter F, right? It wasn't cleared, and the rest of the input was not ignored. That's why I didn't get anything sound here, right? It just didn't work, right? Because the flag was raised, that's it. Scene is not working anymore, right? For that one. So that's why the B didn't get any value, right? And then the exception was not thrown because the quotient is some garbage over here. That's why we see the -0 there, right? You see this -0? Okay. It's not even, okay. Yes, I have to step over here. So step, right? So, the exception was not thrown because the denominator is not 0. So we will see the result as a negative. Okay, come on, display, it's buffering the output. It's not showing it to me. One. Here. Yes. So that's why we see this like -0 over here, right? Okay. So it's nice to be able to work with the debuggers in this way to see what's actually going on in terms of the memory, right? What's assigned to the variable, what value to use. This helps us to catch errors. So that's why I'm showing it to you from time to time. Okay, now if we decide to treat the issues with the input, you see, once again, it will be again about the field beat, right? And clearing the states and ignoring the end of the input. So I'm still not going to throw any errors here. And I'm not going to do it because it's not that much connected to the quotient function, right? The quotient function is about working with two numbers and catching any issues there. And the only issue we can think of is just when we have a denominator 0. So if I decide to process the input separately, raise exceptions and treat them, then instead of this block, I will put another function call. I will call it input, and this is the function that will be, treating the input. And then I can throw exceptions there, and then I can catch them inside the main function. Okay, so something like this in terms of the design, right? Okay, now let's go to the lecture slides back. I'm checking. Okay, we discussed both of them. Okay, so sometimes in some situations, and we have a very good example here, we need to rethrow the exceptions to the function that was kind of calling from the outside. So here is an example. We are working with the file, and an exception occurred, right? Upon this, definitely we want to close the file by the handler, so handler will be taking care of it. But we also want to notify the caller that there was an issue, right? Because obviously when I'm working with the file, it's probably some sub-function that is doing this, right? And we would like to notify the function that called above, right? The parent function, that something happened. So what we can do in this case is we can handle the file and we can rethrow the exception. In this case, we don't need to say exactly what we are throwing. We will just say the throw again. So we'll put in the statement and the exception that was generated will be rethrown again. It's very good. I do have an example, and let me see. Yes, so this is the example when I'm using the exception class. So it's the very, 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 very base class of the exceptions where everybody else inherits from it. So they are children, they are not even the children, but some of them are ancestor, descendants, right, of the exception class. So for example, the runtime error inherits from exceptions. And then invalid argument, no, logic error. Who is, okay, I think logic error, yes, logic error inherits from exception, and invalid argument inherits from logic error. So this is, and runtime error inherits from the exception. I hope my memory doesn't fail me. We have, oh yes, we have a hierarchy here. So let's look at the hierarchy before I proceed. Okay, so runtime error is a child of the exception class. Logic error is the child of the exception class. Bad allocation, bad casting, bad type ID, bad exception, all of them are direct children of the exception class. But the overflow error and underflow error, they inherit from runtime error. So they're descendants of the exception class, or derived classes, right? And the same about invalid argument, length error, out of range. And I think we had another one there, right? So they are all children of the logic error class, right? So they are descendants of the exception class. Once again, it's not all of them here shown, only some of them. And if you are interested in the exception class, then I give the link to it on our web page, so you could see what does it have. There is like a list of the classes that inherit from it. My memory doesn't fail me. Okay, so what's important about all of this is that the exception is the one that has that virtual function what. And if we need to override it in any of our exception classes that we are creating ourselves, we can easily do so, right? We worked with the virtual functions before. Okay, so let's take a look at this example, rethrowing the exception. Let me go to the Visual Studio, delete this one, and let me add the rethrowing the exceptions. So here it is. I am using the exception class now, right? Because this is what I'm going to generate, just the exception here. So it will be just the exception generated over here. And let me see. Yes, so here is the function that I'm going to call from the main function. It just called throw exception. And what it does is it generates an instance of the exception class. So it's defined over here. It's not only that defined, it has more definition, but the base class, that exception class, is defined over here. So this throw exception function, all it does is it throws the exception from itself with no message over here, as you could see. And I do make a comment here that the throw exception function just throws an exception for no reason whatsoever. So I wasn't checking anything, right? I just threw it there. Okay, and then we immediately catch it, right? So we get the access to it, and I have some comments over here. So we caught this exception in this function, not in the main function, right? We caught it in this function, and we throwing it for the parent function, right? For the one that called it, for the function that invoked this method. So because we wanted to demonstrate how rethrowing of the exception works, okay? So once again, the throw exception function throws the exception, catches it, and then rethrows it again. Now the main function tells us that, hey, we are going to call the throw exception function. Then if we see this message over here, then something is not working in the mechanism of rethrowing the exceptions, because if this function throws an exception, nothing after it should be executed. So this is the trick about the exception. If an exception is thrown at this particular stage, nothing else in this block will be executed, but we would immediately proceed to the catch exception and we will try to process it. If the type of the exception matches to what we see over here, then we will process it. But this message will not be displayed. It's a very important thing to understand how the mechanism works. So make sure you got it, like why this cout will not work, right? Okay, so we are catching this exception here. And once again, what type of exception is it? It's a rethrown exception, right? Now we put that we are handling an exception in the main function, right? So once again, we're signaling it to ourselves. We don't do anything here. We just display a message. And then we say that the program flow continues after the try catch block in the main function, right? So I could say in the main function, right? Function, something like that. So let me run it and we could see the entire process of how things were happening. So come over here. So we call the function throw exception. The function call throw exception threw an exception itself, caught it, and re-threw it, right? So all this block over here is kind of telling us what is going on. Now, the main function caught the exception, right? And it said that the program flow continued after this catch block. So we could see the cout statement, right? The program flow continues. Now, do we see this message? If you see this message, then something didn't work? No, we didn't see this message. So it's a very important point, right, to us to understand that if an exception is thrown, everything is paused. Nothing else after that block is executed. So no longer how many lines, right, I put over here, right? Here is another message that should not be displayed if an exception is thrown, right? So no matter what I have over here, I shouldn't see it, right? None of those see out messages that I have over here, right? So nothing of that kind. However, if I had something after this block here, right? And, the exception was not processed over here, the flow of the program will continue, right? So if I did not rethrow the exception over here, the program flow will continue with this line, right? And I would be able to process the code further. Okay. So something like that with the rethrowing exception. So once again, you might find it useful in some of the situations, right? And it's usually when we have a complicated project where we have so many ports that might end up throwing an exception, and it needs to be delivered to the above, to the invoker functions, right above. Okay. So let's go back to the lecture slides. So we talked about rethrowing the exceptions. We talked about the hierarchy of exceptions. And once again, from here, the only ones we saw were the runtime error because I used it, right, today. Logic error we didn't use. Invalid argument we used. And out of range we used, right? But the out of, not the out of range. Yes, out of, no. Yeah, out of range we use, but there was something else there. The other one that we probably use. So that's basically, it, right? Now, what happens in details when the exception is not caught? Because this is interesting thing, right? Like we are catching them everywhere. We were catching the exceptions. We knew what to expect, right? And we were catching them. But what happens if we don't? So here is the plan. If the exception is thrown, but we didn't catch it, in this particular scope where we are right, at the moment, the function call stack is unwound, right? Because you remember how we have this function call stack for all the functions calls, right? So an attempt would be made to catch the exception in the next outer try-catch block. And what we mean here is in the function that called this particular function, right? So in that function in which the exception was not caught, right? So if it terminates, nothing else is going to work, right? If we have after that try block, right? So all local variables that have completed initialization will be destroyed. None of the code will be performed after that, and the control will return to that function that was invoking, right? This one. Now, if the try-catch block is located, we will attempt to process that exception. And if not, we will unwind the function call stack again, and we will try to retrieve the function that called this particular function, right? So we are kind of like 2 levels up now, right? We are trying to see, hey, can you process this exception or not, right? And so forth until the main function terminates, right? Until our entire program terminates. So I have an example here, which I did grab from the book. It was a very kind of visual one because it shows us what's going on with the exception, how it is unwinding, right? So let's go over it and look at it. So once again, this is in a situation where the exception was thrown, but we didn't catch it, right? So we didn't catch it, so we will try to catch it with the invoker function. If it didn't work, we will try to catch it with the more higher level invoker function and so forth. So let me pull up the code for this example. And then let's add stack unwinding. So here it is. Let me skip these functions for now, and let me do this. The main function is calling the function f1, right? And it actually tells us that this function is being called. Now, what we do know in advance is that we are going to throw a runtime error. Just we know about it, right? Like we were building the code in such a way. Because if I didn't know what type of the error is run, I would replace all of this with the 3 dots. Okay, remember that it means any type of exception, right? This is in case if I don't know, right? But I do know. I do know that it will be the runtime error. Okay. So here, in this case, this exception is treated by the main function. And this is what I would say. Exception caught and handled in main function. We will say what was the exception, and then I will say the end of the main function, right? So from the main function, I'm calling the function f1. Let's go to the function f1. Here is the definition of the function f1. It doesn't return anything. It's telling me that it's calling function 2 and it's calling it. And then it tells me that it's the end of the function 1, right? So a very natural process to show that, things are going up there. Now, do you see this comment over here? Let me move it to the next line. Note that the statement will not be executed. Do you remember how I told you, right, that here, over here, right? So all local variables that have completed initialization are destroyed and the control returns to the statement that invoked the function originally. So no statements after this line are executed, right? The control of flow returns to the function that invoked this function, right? So once again, if an exception is thrown inside here, right, I'm not having the catch block here. So nothing after it is executed and the control of the flow is returned to the function that called f1. Okay, so this is what this statement was saying over here. Okay, now we are calling the function f2. Here is the function f2. It does a similar thing. It's calling another function. I'm saying function 3. And I'm also having the C out here that the f2 is over, right? And the same issue here. We will not see this print statement, okay? Because an exception is thrown inside the f3 and it is not caught there. So at this moment, the control of flow will go back to the function that called the f2, and it was f1. Finally, the f3, this is the reason for all our troubles, right? This is the one that threw a runtime error, right? So it threw the runtime error, it didn't catch it, right? So once again, if I write over here, right, the end of function 3, it will not be displayed because the exception is not thrown. So the control of flow will come back to the function that called the f3. So let's run this kind of long program, right, to talk about. So check this out. The main function called the function f1. And the first thing called function, let me see. Yeah, and the first thing the function f1 said is that it's calling function 2, right? Here, like this, right? So calling function 1, calling function 2, right? The f2 is called, where is it? Okay, calling function 3. So this is the third message we see, right? We are calling function 3 and it threw this exception, right? Now, I do see this message, function 3 throwing exception. You see this message, but I don't see this message, right? The end of function 3. So I don't see it after it, but I do see this phrase, exception caught and handled in main function, right? So this is the one that caught it. This is the one that caught it, right? That was the statement that the, right, or the exception. The throwing runtime error in function 3, right? Throwing runtime error in function 3, because this was the message that I supplied here, you see? This was the message that I supplied for the what function, right? And that's it. So this one is not displayed. This one is not displayed. This one is not displayed, right? Only the end of the function main is displayed because the exception was caught and the control of flow follows the main function, right? So that's why we do see this message over here. Okay, so once again, interesting thing to be aware of, just in case if you know, will be working with them at some point in your life, right? Okay, now let me go back to the lecture slides. I think this is it about the exceptions, yes. So here we basically talk about when it could be used and what errors we can come up with. So let me just walk through it because it's just basically just talking. So usually we are working with the synchronous errors to use the exception handling because it is a chain of events that are happening one by one, right? So we process this and then that, and then we perform this step and so forth. So it's kind of a sequential process. So if we have a sequential process, then we could use exception handling, right? So the good examples here will be that we were waiting for the numerator and denominator, right? And something was wrong with one of them, but we're waiting for them, right? Or, you know, maybe we try to allocate the memory. We are waiting for it to be allocated, right? So only then we will work with it. And the memory allocation was unsuccessful. You know, sometimes just, you know, we may run out of RAM, right? And we cannot allocate the memory. So something like that. But we cannot use them when the events are happening asynchronous, right? So it usually happens with something that is called events handling. So we have a system, complicated system of events that happen at different moments in time. They might happen in parallel, you know, they might happen in different moments in time, but they are not sequential. It's very hard then to work with the exception handling here because we cannot predict of what will be the sequence of the events, right? They might happen in a different pattern. So the good examples here is when we are working with the disk input output completion, because we might not wait for the output to happen for a file. We might process something else and work with it, right? So we are not waiting. The network messages arrivals, we never know when will it arrive. Several messages can arrive. They could be processed at the same moment, especially if we have multi-processor machine and so forth. So it really doesn't work very well with the with this process. However, we do have also handling there, but it's not exception handling, it's events handling. So that, you know, these examples over here will be working well with the events handling. So we are waiting for an event to happen and we process, right? So now exception handling gives us a very nice single uniform technique for processing problems. It does help programmers on large programs, on large projects, especially the ones that are not concurrent, right? To understand each other's error processing code. And as I said before, what happens is that usually the companies prefer to use their own exception classes, the ones that were created in particular for them, because they are handling the specific types of the errors, right? Now, it also enables the predefined software components, right, like the standard library classes, to communicate problems to application-specific components. And then, you know, they can process the problems in an application-specific manner. So it's kind of very specialized in this case, right? Now, starting from C++ 11, standard 11, I think I had another comment here. Maybe I forgot to put it. Okay, maybe I forgot to put it, but that's fine. It wasn't a major one. So starting from C++ standard 11, we might opt for the case when we really do not want to throw any exceptions, and we want to enforce it. So what we could add in this case is this keyword no except, right? So it will tell us that it doesn't call any functions that might throw exceptions, and it doesn't throw it itself, right? So in this case, we are kind of enforcing it, right, to be in place. So the person who will be working on it in the future will know, okay, now they didn't want any exceptions to be thrown here. So I just need to work on it as it is, right? Maybe modify the algorithm, but not throw any exceptions. So in case if we also say that our function should not modify like any, attributes of the class, right? Then the no except comes after the const, okay? And we should use it in both the prototype and the definition, okay? So this is just in case if we decided really not to have them and to enforce it. Okay, so what happens with the exception handlings when we have constructors and destructors? Because you see, when we throw an exception, we kind of want to make sure that if we have some memory allocated, right, something there, that it is deallocated properly. So here are some things about the constructors and destructors we can think of. So in general, we do know that constructors do not return a value, right? So we have kind of three options there. One of them, we can return an improperly constructed object if something goes wrong, right? And accept that anyone using it would determine that it's incomplete, and we'll take care of it. Now, another thing, we could set some variable outside the constructor to indicate that something went wrong. Something like a flag, right? Hey, we had an exception there, right? Now, the other option that we actually prefer to use is to throw an exception. So we might require the constructor to throw an exception that contains the information about the error, right? And it will allow the program to handle the failure. So we do allow to throw exceptions from the constructors. Now, if an exception is thrown before the object is fully constructed, the destructors will be called for any member objects that have been constructed so far. And so, and it's, especially it's important because we are allocating memory for them, right? So it must be deallocated. And if we are working with an array of objects, right, we use the dynamic memory allocation and it's partially constructed and an exception occurred, then the destructors for the array's constructed objects will be called, of course, right? Because we need to deallocate the memory that we occupy. Okay, now the destructors are called for every automatic object constructed by the try block, right? Before an exception that occurred in that block is caught, right? So that's another thing. Okay, now what we should not do is we shouldn't throw an exception from the constructor of a global object. You remember the global objects and how they're created, what's their scope, or a static local object, right? Because these exceptions cannot be caught. They're constructed before the main function executes. And that's the reason of why we will not be, able to catch them. Okay, so don't throw exceptions from the construction of constructors of the global object or the static local object. And always keep in mind that whenever we are working with the dynamically allocated memory files, because we are opening them, right, and any other resources that that need to be accessed by another entities, we need to release it, right? So don't forget to do that. Okay, so this is kind of it about the exception handling. Once again, not too deep, not too much, because as I already mentioned, we usually kind of specify the exception classes for our particular goal, right? And let's switch, let's go and talk about the unique PTR, which is connected to the destructors mostly in this case, because what we are doing with the pointers, you remember when we are allocating a memory, we need to release it, right? And you remember that we could have a memory leak if we forget the pointer, right? Like that it points to this memory and we reassign it. Yeah. So now let me see. Yes, yes. So this is like, the conversation about it, right? So we shouldn't have memory leaks. We try to avoid them. And the C++ standard 11 provided us with a unique PTR class. The header to use for this will be the memory. And what it will do is this unique PTR instance will maintain a pointer to a dynamically allocated memory, and automatically, when this unique PTR will go out of scope, the destructor will be called. So I don't need to do delete statement. Delete statement, if you remember when we only allocate one space, right, for one item, and the delete with the square brackets, it's for the built-in array, right? So they will be called automatically when the unique PTR goes out of scope. Excellent, right? So I don't need to bother with making sure that the place was deallocated. They do provide the operators to work with the unique PTR. So the dereference is working, right? And the one which is dereferencing calling method, right? Remember, right, that the arrow that we used? So it could be used just as any other regular pointer object, right? But now we don't need to care about the memory deallocation. Now, there are some limitations, of course. Only one unique PTR at a time can own a dynamically allocated object. So only one, because it's unique, right? It stands from the name, it's unique. When assigning one unique PTR to another, first of all, I cannot just say PTR1 is equal to PTR2 because that operation is not defined. I'll have to move, right? So it's kind of, I'm moving the ownership, right? So the one on the right then will be transferring its ownership of the dynamic memory it's managing to the PTR on the left, right? And once again, I cannot just say that it's equal. We will do it in the example. Just, bear with me for a moment. So I'll have to use the function move. Now I could pass a unique PTR as an argument, but in this case, the ownership will be transferred as well. So that, that one I don't have an example about, but it's pretty clear how to do that, right? And then the last unique PTR object that maintains the pointer to the dynamic memory will be deleting it when unique PTR goes out of scope. So it's very, very nice. Now, in order to demonstrate the work of the unique PTR, I had to use a class. So the book used a class, and I, kind of followed the same way. It's a very silly class. What it does is it tells me, hey, constructor is called. Hey, destructor is called. So it's sending me the messages of what's going on about the object. And it has only one attribute there, like a number, one, data attribute. So let me pull them up. And this will be our last example for today. So it's a very good timing for us. Remove. And then let me pull up those two files. So I have a header class, and you know what? I defined the entire class in the header and the unique PTR example. Okay, so check out this class. I called it some class. I don't remember how the book called it. Now I do define a friend output operator, right? So I'll be able to see out the objects of this class. And I also define the operator of assignment, right? So, and I did allow the chaining. So I could have multiple assignments there. Now, when I'm assigning one some class object to the other one, just the value is, oh, no, it's not assignment of the object. It's only assignment of the value. Sorry, right? Yeah, I didn't define that one. So it will be just the built by default. Now, so here I'm assigning an integer value to the sum class object, right? And what will happen is the value that is stored right now in the object will be replaced by the new value, right? Okay, so only one data attribute, integer value. Now the constructor just tells me that the constructor is called, and the destructor doesn't release any memory. No, it just tells me that the destructor is called, right? So like, something simple. And then since it's a header file and I'm not including the standard namespace, I have to use the std scope resolution, right? So don't forget that one. Now, this output I defined right here in the header file, because once again, it's only 2 lines of code, so it's not very clumsy. And I just put it out of here. So I do have access to the sum class object, although I say that I should not modify it. But all I do is I output the value, right? And then I return the reference to the output stream again. So this is a standard thing that we did before. I'm not inventing anything here. And so I'm not defining too many things over here, just kind of 3 things, like 1, 2, 3 in terms of the operators of the class, and just redefining, overloading the output, right? Okay, now what do I do with the unique PTR? I do create 2 unique PTRs. They will be different. They will be pointing to different objects, but I do the assignments differently. I just wanted to show them to you. So don't forget to include the memory header. Now, one PTR, I say I create by doing this. Now, I say make unique. What's the template type, right? Because make unique is a template function. It's grabbing the type of the object I'm thinking of, and the 12 is the initializer for it, right? Because you remember it requires 1 parameter. I could put it by, I could use the default parameter, but I provided it with the value of 12. So make unique is a function that creates an object. It's dynamic allocation, so it's the same as I would say PTR1 is equal to new, right? So it's absolutely the same thing, sum class of 12. It's absolutely the same thing, but this dynamic allocation is prohibited with the unique PTR objects. So you could see that this operation is undefined. Come on, show me the message. Show me the message here. So this is not defined to work with it, right? So operator equality does not match to what I have over here. This is what we used to do when we were dynamically allocating memory. So for example, like I would say new int, right? And then maybe it's, well, like, something like that, right? So it's not working with the unique PTR. That's why I had to use this function, right? That dynamically allocates a space for an object of type sum class, which is, provided with the 12 as an argument. That's kind of, the only way for me to do it. I cannot use the new command. Okay, there is another way to use the new. So this is another one. If I really want to use that new, what I can do is I could say that I'm resetting the pointer, right? So I'm resetting the pointer to point to this instance of the sum class. Okay, so this is how I could use it, right? But then I also, so all these commands, reset and make unique, they're all about the unique PTR, right? These are the ones that are returning. So make unique, returning the unique PTR to the memory, and reset is a member function of the unique PTR object, right? So only 2 ways for me kind of to do that. Okay, so now this is what I do next. I see out them, right? Since I overloaded the output of the sum class objects, when I am dereferencing the unique PTR1, the unique PTR2, it will display me the objects of the type sum class, right? So it should show me the values of 12 and 14, right? With the space, right? And the end here. Okay, now this is the reassignment. So for this particular 2 lines, that's why I defined the assignment operator, right? So I overloaded the assignment operator for the sum class. I said, how will it work on this, right? So this is for these 2 lines. And then I decided, right, that I should move some things from one pointer to another. So I want to do this reassignment. So I couldn't do this, right? I couldn't say that now PTR1 will be having the information of what the PTR2 was pointing. Once again, because this equality is not defined for them. So the only thing I could do is I could use the move membership, right? No, membership, ownership, right? I could use this move ownership. And I had to do it with the STD. Oh, no, I don't need to do the STD. Okay, so just like this. Right, so I'm using the move ownership of the PTR2 to the PTR1. Now, guess what? Guess what? The PTR2 lost its ownership of that object, right? So it's no longer referencing, you know, it's a changed value there, we will see, right? But it's no longer referencing that second object, right? The PTR1 is referencing it. So what do you think happened to the object that the PTR1 was referencing before? Well, you will see that it will be deallocated. We will see the confirmation by having this one. The structure is called, right? So that first object should be destroyed because we are losing any information about it. So the unique PTR takes care of it. Isn't it wonderful, right? So let me mark this one out. I'll comment it out because I'll use it later on to show you a little bit more. I just want to show you that we moved the membership. So we moved the ownership. Why am I saying membership? Ownership of PTR2 to PTR1, right? You know, let's do it this way. Okay, so check this out. I'll move it over here and we can go to the very beginning. So we're creating two pointers, but here the constructor of the sum class will be called. Do you see this message? Constructor is called, oh, constructor. Okay, I have a typo there. Okay, constructor, right? Constructor. Let me constructor, right? Constructor is called. It's okay. I'll have to update the files on our website later. Okay. This is the second call to the constructor. So this is for this new element, right? So this new object. So another object of some class. Then the values right now are 14 and 12, right? 12 here, 14 here. So these are their values. But then we change the values, right? Through the pointers. So here are the changed values. Do you see this message? Destructor is called, right? Destructor is called. It happened right here in this line. I'll show it to you again. Because this message came after, right? It came after that. So when I was moving the ownership of the PTR2 to the PTR1, the object of the PTR1 had to be destroyed because otherwise we will lose any access to it, right? So that's why we see this destructor, okay? And then after we moved the ownership of PTR2 and we displayed this message, it was the end of the program. So the destructor was called automatically for that second object as well, right? So you see that I did not call any deallocations here, right? They were done automatically. Excellent. So now let's proceed over here. Let's uncomment this one. This is a very silly example of what will happen with the built-in array, because we can do it as well. We can direct our unique PTR to point to an array of 20 integers. So take a look at how do I do it. I didn't say equals to, I could, right? It's not a big deal. I just say that initialize it, right, with it. Okay, so I have this name, PTR array, right? It's the name of the unique pointer. This unique pointer, I'm telling it, hey, you know what? You'll be pointing to the array of integers. So I'm using the square bracket here, right? So I am allocating, well, I'm not, make unique. Make unique will allocate the space for 20 integers, right? over here, and it will return the unique pointer to the PTR. So PTR points to the very beginning of the array of 20 integers. Now using it, I'm going to initialize them, right? So I'm going to put into each ith position the I plus 1, right? So in other words, we will be having 1, 2, 3, 4, 5, 6, 7, and so forth there, right? And then later on, I decided to change the value of the element at the 9th position to 23, right? Right now, it should be like 10 there. I think it's the value is 10, right? We could put it out. Okay, the value at the 9th position, right, is, and let's say, what is it? PTR array of 9, right? And L. And then we are replacing it with the 23, and then we show what's going on. Okay, so here, the value at the 9th position is 10, right? Because I was adding 1. Do you see this one? I plus 1, right? So it was adding 1. And then we changed it to 9. And then check this one out. Destructor is called, right? This destructor message is for the PTR1, right? So after we transferred the map, the ownership, right? The PTR here leaves, right? So it leaves through this stuff, and only by the end of the program, when it terminates, the destructor is called. So this message is for that object with the value of 50, right? This one was for the object with the value of 23, and this object is for this. We can even add it into the message destructor. Let me see. Destructor is called for the object with value of, let's see, let's do it like this. Of value, and then and now like this. This one would be better, right? This one would be better. Here, you see, so destructor is called for the object with the value of 50, and here destructor is called for the object with the value of 23. So after we moved to the ownership, right, it was transferred and the object was destroyed. Okay, so once again, unique PTR is quite often used because we have less issues with it, and it always makes sure that the place is deallocated. So we quite often opt for use of unique PTR, not the usual pointers. Okay. Wait, sorry, I pressed the Control S. Okay, so this is it. This is it about the pointer, unique pointer, and the exception handling. Now, you do know that I'm not giving you any homework assignments. I am working on the assignments that you were submitting me so far, but I'm giving you something for practice. So in number 1, I'm asking you to look at the program and try to predict what will be the output without running it, right? Just looking at the code. If, we run it, and if for the values, we will provide the value of 4 and 0, right? Now, this one is about the exception handling. Apologies. No, this one is this one. This one is about the exception handling. Now, the second one is about the unique PTR. Same thing. Try to predict without running on the program what will be the output when the program is run, right? So these are the first two, like I was kind of able to come up fast. Of course, we need to do a little bit more practice to understand them much better. So definitely what I would recommend is to go over all the examples that we had today. Try to type them in, on your own, see what's going on, what happens if you change this, or the other thing. Now, for the self-study, there is a section that I didn't cover. It's a section 17.8. Look at it. It's a small one. It doesn't have a lot of the stuff in it, but it's very it's worth looking into it for sure. It will be recalling the null PTR that we talked about before. So it's also will be some kind of a review for you. And in terms of other suggested practice, look at the summary and the self-review exercises at the end of the chapter. The only thing that I kind of regret is they have the questions, but they don't have like the really like practice with the answers. So unfortunately, that's why I gave you these two, right? And if I come up with a little bit more, then I will put them as well. But so far on our website, I'm telling you just to look into the lecture slides to see these two, practice problems. Okay, and you can also, check yourselves for the answer, because you can copy and paste it into your compiler and run it to see what's going on. Were you able to predict it correctly? Okay. Tutor tomorrow, yeah. Okay, so let me stop the record.